Hello, I just want to review solving trigonometric equations with you, and in order to help us do that, let's just review real quickly the unit circle. It will be helpful if we can quickly imagine what the trigonometric values are at each of the angles that we have memorized on the unit circle. So let's just, it's not going to be a beautiful unit circle, but what helps me is to think about my Cartesian coordinate system, and I'm just going to label the angles that I have memorized in the first quadrant. I know that this is the angle pi over 6, and at pi over 6, the ordered pair is where x is almost 1, x is square root of 3 over 2, and y is a half. At pi over 4, I know that both coordinates associated with that angle are square root of 2 over 2. And then at pi over 3, the y is almost 1. So y is square root of 3 over 2, and x is a half. So when I'm solving trigonometric equations, I can refer to this very rough depiction of the unit circle and answer questions like, what is the angle whose sine is a half? Well, sine is the y-coordinate, and the angle whose y-coordinate is a half is pi over 6. So I would say the solution of that equation, at least in the first quadrant, is pi over 6. It also may be helpful to me to make a note of what the coordinates are of each of the ordered pairs in the second, third, and fourth quadrant. In the second quadrant, I know that all my x's are negative and my y's are positive. That means in the second quadrant, cosine is always negative and sine is always positive. In the third quadrant, both coordinates are negative, so both cosine and sine are always negative. And in the fourth quadrant, my x's are positive, but my y's are negative. That means in the fourth quadrant, cosine's positive and sine's negative. Now, the examples that I have chosen are from section 6.2 in the Precalculus book. We're solving trigonometric equations. And you need to pay attention to the directions when you're solving trigonometric equations. The first equations the first directions in this section say find all solutions of the equation. And that means in infinitely many revolutions of the unit circle. If I ask you where sine is 1, that means where y is 1, and we know that y is 1 on the y-axis where x is 0. That's the angle pi over 2 where x is 0 and y is 1. So if I said solve the equation sine x equals 1, there's only one angle in one revolution of the unit circle whose sine is whose sine is 1, and that's the angle pi over 2. In one revolution of the unit circle, that's the only angle whose sine is 1. But there are infinitely many coterminal angles with pi over 2. I could add pi over 2 plus any multiple of 2 pi radians, and I'd be right back at the same angle where sine is 1. So when the directions say find all solutions of the equation, it means in infinitely many revolutions of the unit circle, and we'll have to talk about how to write that, how to indicate in your solution that you have all infinitely many revolutions of the unit circle. All right, I wish there were some magic steps that I could give you for solving trigonometric equations. I can give you some hints, some things to think about, but unfortunately there are no magic steps. The first hint, or the first method I'm going to use, and I just made this up, but I'm going to call it squint and solve. You just literally squint at the equation, picture in your mind the unit circle, and solve the equation by thinking of the angle whose sine or cosine or trigonometric function it is that you've asked for. For example, number 2 says cosine t is -1, and that means I'm looking for all the angles where cosine is -1. First thing I need to think is cosine is the x-coordinate of angle t, so where is x -1? And here's the mental image that I have. The only place that x is -1 in one revolution of the unit circle is right here at pi radians, where x is -1 and y is 0. So in one revolution of the unit circle, the only place where cosine is -1 is at pi radians. Now t is the angle, pi is the angle measured, pi radians. If I check that by substituting pi back in the place of t, then I have cosine of pi is -1, and that's a true statement. In one revolution of the unit circle, that's the only angle where cosine is -1. But because the directions here say find all solutions, I want to add to that all the coterminal angles. Now remember how to get coterminal angles. All the angles that will end right here, you get coterminal angles by adding revolutions of the unit circle. If we were in degrees, you would add all multiples of 360 degrees would land you in the same spot. But since we're talking about radians, instead of 360 degrees, we're going to use 2 pi radians. Adding multiples of 2 pi radians will land us in the same spot. So I can write all solutions as pi plus all of its coterminal angles, and all of its coterminal angles are 2 pi n, where n stands for any whole number and I still can check my answer by saying if n is 0, then t would just be pi. 2 times pi times 0 is 0. 0 plus pi is just pi. And we've already checked that when t is pi, this equation's true. Now when n is 1, this would be 2 pi plus pi is 3 pi. If we let t be 3 pi, then cosine of 3 pi is also -1. Cosine of 5 pi is always also -1. Anytime we are at pi and at all the coterminal angles, cosine of that angle is going to be -1. So this is all the solutions to that equation. Now this is going to take practice. I can tell you this is one of the most difficult things in trigonometry is solving trigonometric equations, but the only way that you get better is practice. So let's see some more examples. Number 4 says cotangent alpha is -1 over square root of 3. Almost any time you give me an angle, an equation involving cotangent or cosecant or secant, I'm going to try to change that equation to one of the 3 trigonometric functions for which I'm more familiar. I'm going to try to change it to either sine, cosine, or tangent just because I deal with that better in my head. So if you give me cotangent alpha is negative 1 over square root of 3, I know, because cotangent's the reciprocal of tangent, I know tangent of alpha would have to be negative square root of 3 over 1, or just negative square root of 3. I also know that tangent is the y divided by the x. So I'm looking for the angles where the y divided by the x is negative square root of 3. Now, where is tangent negative? If tangent's the y divided by x, you just need to ask yourself, where is y divided by x going to give you a negative? Well, it's going to give you a negative in quadrant 2, where you have a positive divided by a negative, and in quadrant 4, where you have a negative divided by a positive. So I know that in one revolution of the unit circle, I'm going to have solutions in quadrant 2 and in quadrant 4. And I know to get a square root of 3, in quadrant 1, the only two angles that have a square root of 3 are pi over 6 radians and pi over 3 radians. I just need to think which one would the y divided by the x give me square root of 3. Well, the pi over 6, the y divided by the x, the way you divide by a fraction is to flip the fraction and then multiply. That would give me 1 over square root of 3. That's not what I want. I want just square root of 3. So pi over 3, the y divided by the x. Flip the x, the 2's would cancel and leave me square root of 3. So in the first quadrant, if this were tangent alpha is positive square root of 3, then the solution would be pi over 3. Since we're looking for where tangent is negative square root of 3, and we've already determined that's in the second and the fourth quadrant, I just want the two reference angles in those two quadrants. The pi over 3 in the second quadrant, here's pi over 3, let me just put that. Pi over 3, the coordinates are 1/2 and square root of 3 over 2. In the second quadrant, that same angle would be, this is 1/6, 2/6, 3/6, 4/6, or 2/3 pi, and then 5/6, 6/6, 7/6, 8/6 in the third quadrant, 9/6, 10/6, better known as 5/3 pi in the fourth quadrant. So tangent alpha would be negative square root of 3 at 2/3 pi and at 5/3 pi. It would be positive square root of 3 here and here, but we want the solutions, the angles whose tangent is negative square root of 3. So it's these two angles, and the question is, if I write alpha equals 2/3 pi, can I write all of the other angles as being coterminal angles with this? Well, I could write 2/3 pi and all of its coterminal angles, and then 5/3 pi and all of its coterminal angles. Or I could just notice that if this is the first solution, I can get all the other solutions to this equation just by adding 180 degrees. If I keep adding 180 degrees, I'll continue to bounce back and forth between this angle, this angle, this angle, this angle, this angle, this angle. Now I said 180 degrees because that's easier for most folks to think, but we're dealing with radians here. So instead of adding 180 degrees, I'm going to add pi radians, and I want infinitely many multiples of pi radians. So 2/3 pi plus 180 degrees, or 2/3 pi plus all the multiples of 180 degrees, all the multiples of pi radians, will give me all of the angles whose tangent is negative square root of 3. That's all of the angles whose cotangent is negative 1 over square root of 3. And that's what we were looking for. Now, when I say squint and solve, this is literally what I'm doing in my head, if I can do it in my head. If I can't do it in my head, then I'm going to draw this little picture. The more you practice, the less you have to draw this picture. But when I was very first solving trigonometric equations, drawing the picture of the angle whose cotangent was negative 1 over square root of 3, or the angle whose tangent was negative square root of 3, was just about the only way that I could solve these equations. With lots of practice, I could do this picture in my head instead of on paper. All right, number 6. Solve the equation cosecant gamma is square root of 2. And as I mentioned, if you give me an angle involving cosecant, an equation involving cosecant, probably the first thing I'm going to do is change it to an equation involving sine. If cosecant is square root of 2, then sine of gamma is the reciprocal of that, 1 over square root of 2. Sine is my y-coordinate, and if I think about my unit circle over here, I don't have any of those y-coordinates being 1 over square root of 2, but I know that if I rationalize that, I get square root of 2 over 2. So now we're just solving the equation sine of gamma is square root of 2 over 2. Now, how many times in one revolution of the unit circle is sine of an angle positive square root of 2 over 2? If that's the y-coordinate, the only two quadrants in which the y-coordinates are negative is, this is difficult enough to do and write and talk at the same time. I'll try to do a better job, but y'all might have to forgive me for stuttering just a little bit. In what two quadrants is sine positive means in what two quadrants are the y-coordinates positive. And we know that the y-coordinates are positive in the first and the second quadrant. So I'm going to have solutions in both the first and the second quadrant. I also know that my y-coordinates are square root of 2 over 2 at a quarter pi. So here's what I'm picturing. I have a solution in the first quadrant. It's pi over 4. And I have a solution in the second quadrant, 1/4, 2/4. This is 3/4 pi. Those are the two angles in one revolution of the unit circle where sine is square root of 2 over 2. So gamma can be pi over 4. And I'm wondering if I could write all solutions as I did in number 4. Just take the first solution and add multiples of 180 degrees. Let's see if it works with this equation. If we start at pi over 4, we can just add 90 degrees and we'd be at the 3/4 pi. So maybe I should write this as pi over 4 plus multiples of 90 degrees. Or since we're in radians, pi over 4 plus multiples of pi over 2. Pi over 2 is the same as 90 degrees. The problem with that is if I started here and added multiples of 90 degrees, I would not only pick up this second quadrant angle, but the next time I added a multiple of 90 degrees, I'd pick up a third quadrant angle, and sine's not positive here. That wouldn't be a solution. If I added another 90 degrees, I'd pick up a fourth quadrant angle. Sine's not positive in the fourth quadrant. So when dealing with sine and cosine, I need to write these solutions separately. I want to say gamma is a quarter pi plus all of its coterminal angles, or gamma is 3/4 pi plus all of its coterminal angles. Now, one thing you will notice here when we were dealing with tangent, we added multiples of pi. That's because the period of tangent is pi. Tangent repeats itself every 180 degrees. Tangent repeats itself every pi radians, so we're adding multiples of pi radians. But sine's period is 2 pi. It doesn't repeat itself every 180 degrees. It repeats itself every 360 degrees. And that's why we have to add multiples of 2 pi when dealing with sine and cosine. Only add multiples of 1 pi when you're dealing with tangent. All right. Number 8. Cosine of x is negative pi over 3. It's very easy to get mixed up about what it is you're solving for here. We're looking for the angle. Solve for x. X is the angle whose cosine is negative pi over 3. Now, is that the same thing as x equals cosine of negative pi over 3? That's a question mark. We're wondering if these two equations mean the same thing. Well, cosine of negative pi over 3, I could say negative pi over 3 is pi over 3 units clockwise from the x-axis. And I could tell you the cosine of negative pi over 3. I could tell you what x would be right there. It would be a half. Cosine of negative pi over 3 is a half because x is pi over 3 there. Excuse me, x is a half here. This is not the same thing. Here I'm given the angle. Here I'm looking for an angle. I'm looking for an angle whose cosine is negative pi over 3. Certainly, if I look at my angles in the first quadrant, none of those angles have a cosine being negative pi over 3. None of them have an x-coordinate being negative pi over 3. That makes me wonder what the solution to this is. I know that cosine is negative in the second and the fourth quadrants, but even in the second and fourth quadrants, none of those x-coordinates are going to be negative pi over 3. What's the smallest thing cosine can be? The very lowest value of cosine. The very lowest value of cosine occurs right here where cosine is negative 1. Negative pi over 3 is less than negative 1. If I enter that on the calculator, I get negative 1 point something. This is negative 3.14 divided by 3. That's less than negative 1. Cosine is never less than negative 1. So this equation has no solution because cosine of x is always between negative 1 and 1. It's never less than negative 1. Negative 1 is the smallest thing cosine can be. So there is no angle whose cosine is negative pi over 3. Number 10 is cosecant theta times sine theta equals 1. First thing I notice is cosecant theta is the same as 1 over sine theta. So I can just make that substitution. Cosecant theta is 1 over sine theta. That's not technically always true. Cosecant theta is 1 over sine theta wherever sine theta exists. But where sine theta doesn't exist, where sine theta is 0, cosecant theta doesn't exist. So this substitution that I did is only valid if sine theta is not equal to 0, because where sine does equal 0, cosecant is undefined. Where is sine 0? Sine is your y-coordinate. Your y-coordinate is 0 on the x-axis at 0 radians and at pi radians. Or I could say 0 radians plus all the multiples of pi radians. In other words, sine is 0 at all the whole pi's. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So sine is not equal to 0 anywhere except pi n. When you think about solving this equation, it's tempting to say 1 over sine times sine is always 1. That's always a true statement. Anything times its reciprocal is 1. But you have to remember that you have to exclude all the values where sine is 0. That's all the values of pi n radians, all the angles which are multiples of pi radians. So that's true for all angles, and here our angle is theta, all angles except multiples of a whole pi. Anywhere else, anywhere other than your multiples of whole pi, cosecant times sine is going to give you 1. All right, I have just a few more examples of these that we're just squinting and solving, and then I'll show you another tool that we use sometimes. Number 14 is cosine of 1/4 x is negative square root of 2 over 2. And I know that this square root of 2 over 2 occurs at multiples of pi over 4, my quarter pi's. And I know that cosine is negative in which two quadrants? Where is cosine negative? In the second and the fourth quadrant. So I just need the quarter pi that's in the second quadrant and the quarter pi that's in the third quadrant. In the second quadrant, this quarter pi is 1/4, 2/4, 3/4 pi. And in the third quadrant, that's 4/4, 5/4 pi. So in one revolution of the unit circle, those are the only two angles where cosine is negative square root of 2/2. I'm tempted to say that x is 3/4 pi plus all of its coterminal angles. All the other angles that stop with its terminal side right there are multiples of 2 pi n, or x is 5/4 pi plus all of its coterminal angles. The thing is, this wasn't just cosine x. This is cosine 1/4 x. So these two solutions here are the angles which a quarter of those angles is 3/4 pi plus 2 pi n, or a quarter of those angles gives you 5/4 pi plus 2 pi n. In calculus, when we don't just have cosine x, we have cosine something else. I'm going to call that something else. You'll hear this a whole lot in calculus. I'm going to call that something else. That's cosine ugly. We're not solving here in the beginning. We're not solving just for x. We're solving for ugly. So ugly is 3/4 pi and all of its coterminal angles, or ugly is 5/4 pi and all its coterminal angles. There's only one step that remains in solving for x. If I gave you this equation in algebra and said solve for x, you would just multiply both sides by 4. I wish I had a colored pen here, and I don't. So this is going to look bad with a Sharpie, but multiply both sides by 4. So that on the left-hand side, those 4's cancel, and you're left with what you actually want, which is just x. You're not solving for quarter x, you're solving for x. On the right-hand side, make sure you distribute that 4 completely. 4 times 3/4 pi is just 3 pi, plus 4 times 2 pi n is 8 pi n. The second solution, or second group of solutions, would be x equals, again, distribute the 4 completely. You get 5 pi plus 8 pi n. And these solutions are checkable. You can let n be 0 here, and you just have x is 3 pi. If you put 3 pi in the place of x, you'd have cosine of 1/4 times 3 pi, or cosine of 3/4 pi is negative square root of 2/2. Well, certainly that's true. If we let n be 0 here, we'd have 5 pi. If we put 5 pi in place of x, we'd have cosine of 5/4 pi is negative square root of 2/2, and that is also true. Then we could let n be 1, and we'd have 11 pi here and 13 pi here. You could verify that both 11 pi and 13 pi are angles whose cosine of 1/4 of that is negative square root of 2/2. All right, number 16. Cosine x minus pi over 3 equals negative 1. If you just ask me where cosine is negative 1, in one revolution of the unit circle, there's only one place where x is negative 1, and that's right here at pi radians. Now, if this was just cosine x is -1, the answer would be pi. But it's not just cosine x, it's cosine ugly. So instead of saying x equals pi radians, we're going to say ugly. Whatever it is, ugly is pi. And since we're looking for all of the solutions and infinitely many revolutions of the unit circle, we need to add multiples of 2 pi in. That's not what x is, that's what ugly is. To solve for x, all we have to do is add pi over 3 to both sides. And notice that when you add pi over 3 to both sides, on the left-hand side, that leaves you the x just like you want. On the right-hand side, you just combine like terms. You're adding pi plus pi over 3 because those are like terms. This is 3/3 plus 1/3 is 4/3 pi plus 2 pi n. 4/3 pi plus all the revolutions of, 4/3 pi plus all of the coterminal angles in infinitely many revolutions of the unit circle. All right, I only have one more of these before I'm going to give you another hint or tool that you may need to use sometimes. Number 20 says cotangent theta plus 1 equals 0. Actually, I just noticed I'll need the hint on this equation. So let me go ahead and tell you what the hint is. Sometimes the first thing I need to do is isolate the trig function. On number 16, the cosine, the trig function was already on a side by itself. You have cosine of x minus pi over 3, but that's all one function, and it's all that's on the left-hand side. On number 20, I can get cotangent theta by itself by subtracting 1 from both sides of the equation. I can get the trig function by itself, and I'll have cotangent theta is -1. If cotangent theta is -1, then tangent theta is the reciprocal of that. The reciprocal of that is still -1. So how can I get tangent is -1? Tangent's a fraction. It's the y divided by the x. How can you get -1 when you divide two numbers? The only way you get -1 when you divide two numbers is if the two numbers are opposites of each other. Where does that happen on the unit circle? Where are the x's and y's exact opposites of each other? It would definitely be in the second and fourth quadrants, and it would be at the quarter pies in those two quadrants. In the first quadrant, if you at a quarter pi, if you divided the y by the x, you'd get +1. But in the second quadrant quarter pi, better known as 3/4 pi, if you divided the y by the x, you'd get -1. And that same thing would happen at 7/4 pi. The y divided by the x would give you -1. So I could list those solutions separately. I could say 3/4 pi and all of its coterminal angles, and then 7/4 pi and all of its coterminal angles. But remember, the period of tangent is pi, 180 degrees. So I can write this solution just as 3/4 pi plus all multiples of 180 degrees, or all multiples of pi radians. And you can check that solution by letting n be 0. If n was 0, this would just be 3/4 pi, and cotangent of 3/4 pi is -1. -1 plus 1 is 0. If you let n be 1, then this would be 7/4 pi. Cotangent of 7/4 pi is -1. -1 plus 1 is 0. All right, I promise you that this gets easier with practice. I can almost promise you that it will be very difficult when you first attempt solving trigonometric equations, but it's vital in calculus anytime we find a derivative, whatever that means. We find a derivative, we set it equal to 0, we solve that equation. And since some of our functions are going to be trigonometric functions, we're going to be solving trigonometric functions a lot in calculus. All right, another example where you might need to isolate the variable. Number 12, backing up just a little bit, number 12 was 2 sine of 3 theta plus square root of 2 equals 0. When I say isolate the trig function, I'm talking about get the sine of 3 theta by itself. If you call that whole thing your ugly, that's just like solving 2, I use u for ugly, that's just like solving 2u plus square root of 2 is 0. I'm just letting that whole sine of 3 theta be some ugly for a minute. And if I told you to solve that for u, you would know that first you had to subtract square root of 2 from both sides and then divide by 2. That's exactly what I need to do here. I need to subtract square root of 2 from both sides and then divide both sides by 2. And I have isolated the trig function. Now I can't divide both sides by 3 here, but I could do it, but it wouldn't help me solve the equation, because if I divided both sides by 3, I couldn't cancel my 3's. This 3 is not a coefficient of sine, it's the coefficient of theta. So I just need to think, where is sine negative square root of 2 over 2? Where is sine negative? In what 2 quadrants is sine negative? Sine is negative in the 3rd and the 4th quadrants, and it's negative square root of 2 over 2 at the quarter pi in those 2 quadrants. This is 5/4 pi, and this is 7/4 pi. So in one revolution of the unit circle, those are the 2 angles whose sine would be negative square root of 2 over 2. Remember, I'm going to have to write these solutions separately. I'm going to have to say 5/4 pi and all of its coterminal angles, and 7/4 pi and all of its coterminal angles. That's not what theta is, that's what 3 theta is. 3 theta is 5/4 pi plus all of its coterminal angles, or 3 theta is 7/4 pi and all of its coterminal angles. To solve for theta, just divide both sides of both equations by 3. theta is 5/12 pi plus 2/3 pi n for the first set of solutions, or theta is 7/12 pi plus 2/3 pi n for the second set of solutions. I have one more, and then I'll show you another trick that you might have to use. Number 26 is asking us to solve 3 minus tangent square beta is 0. The way I got through a lot of trigonometry and a lot of calculus is to say, if that's so ugly it scares me, I can make up something simple just like it. If you ask me to solve 3 minus ugly squared is 0, and ugly is just some variable, I could use the square root method. I could add u squared to both sides, and then I could take the square root of both sides, not forgetting that when I take the square root of both sides, I get both a positive and a negative solution. So if this were the equation I was solving, I'd have 3 equals u squared, where u is positive or negative square root of 3. This is the same thing with tangent beta in place of u. And I solve it the exact same way. I would add tangent square beta to both sides, and I would take the square root of both sides, not forgetting that I get both a positive and a negative solution. I'm going to turn this around. I'd rather have the tangent on the left-hand side. So tangent beta is positive square root of 3 or negative square root of 3. I know tangent's the y divided by the x, so I just need to think where on the unit circle would the y divided by the x give me square root of 3. Where in the first quadrant would the y divided by the x give me square root of 3? Well, at pi over 6, the y divided by the x, flip the x, the square root of 3 is going to be in the denominator, and that's not what we want. At pi over 3, the y divided by the x, you flip the x, the 2's cancel, the 3 would end up in the numerator like you want. So pi over 3 is one angle where tangent is square root of 3. And I know there would be a fourth quadrant angle whose tangent was also pi square root of 3. And I know there would be a second and fourth quadrant angle whose tangent was negative square root of 3. So there are 4 solutions here. What's the simplest way I can write all 4 solutions? Well, I could start with the first solution, pi over 3, and I could add 180 degrees or pi radians to get all of the first and third quadrant angles where tangent would be positive square root of 3. But then I'd have to write another solution as this is 263646 or 2/3 pi and infinitely many multiples of pi n would give me all the second and fourth quadrant angles where tangent is negative square root of 3. So one of these solutions gives me all the angles whose tangent is positive square root of 3. The other solution gives me all the angles whose tangent is negative square root of 3. All right. I'm going to give you one more hint that we need to use to solve number 34 and some other trigonometric equations. 34 is tangent alpha plus tangent squared alpha is 0. "34 is like, if we just call tangent alpha ugly, this is ugly, and this is ugly squared. Ugly plus ugly squared equals 0. What kind of equation is that? If it was x plus x squared, and I said, what kind of equation is that? You would say, well, because there's an x squared, it's a quadratic equation. As a matter of fact, number 26 was a quadratic equation. It was a quadratic equation that we could solve by taking the square root of both sides, by using the square root method. That trick won't work on number 34, but there's another way that we know how to solve quadratic equations, and that's by factoring. This simple equation, we'd factor out a u and then set each factor equal to 0. Well, we can do the same thing in 34 by factoring out a tangent alpha. And you factor out a tangent alpha, just like you factor out a u. You say, what do you multiply times tangent alpha to get tangent alpha? And that's just 1. For the second term, what do you multiply times tangent alpha to get tangent squared alpha? That's tangent alpha. Distribute tangent alpha, and you will get back what you started with. To solve a quadratic equation, you can factor it and then set each factor equal to 0. And that gives us 2 linear equations to solve. The first one, tangent alpha is 0. Where is tangent 0? On the unit circle, it's wherever the y divided by the x is 0. Would that be at 0 radians? Would that be at the ordered pair 1, 0? Or would it be at pi over 2 radians? At pi over 2 radians, what's tangent? The y divided by the x is undefined. The 1 divided by 0 is undefined. We're looking for where tangent is 0. That's right here at 0 radians. 0 divided by 1 is 0. So alpha could be 0 radians, and not only at 0 radians, but at pi radians. 0, at 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, all of the multiples of pi radians. So instead of 0 plus pi radians, a simpler way to write that would just be all the multiples of pi radians. Any angle which is a whole pi would make this original equation true. The second equation, if we solve for alpha, we'd have to subtract 1 from both sides, and then think about the angle whose tangent is -1. Well, I know that tangent's -1. Tangent's negative in the second quadrant, where the y divided by x is negative, and in the fourth quadrant, where the y divided by the x is negative. And that would have to be the quarter pi angles in those two quadrants, because at the quarter pi angles, you'd have negative square root of 2 over 2 divided by positive square root of 2 over 2, or vice versa. This is 3/4 pi and 7/4 pi. You could get off those angles by just saying alpha is 3/4 pi plus all the multiples of 180 degrees, all the multiples of pi radians. So pi n would give you one set of solutions. 3/4 pi plus pi n would give you another set of solutions. All right. I have just a few more that I want to factor. I'm doing so many examples because I know this is going to take a lot of practice. But let's switch to the problems that say, find the solutions that are in the interval 0 to 2 pi. Notice 0 radians is included, 2 pi radians is not included. That's just one revolution of the unit circle. Instead of talking about find the solutions in infinitely many revolutions of the unit circle, we're only looking for the solutions in one revolution. So that means we're not going to have to worry about the plus 2 pi n or the plus pi n. All right, I have, let's see, try to finish this up a little bit more quickly. Let me just do two examples, number 42 and 44. What kind of equation is that? If we think of the cosine t as being our ugly, then that's just like 2 ugly squared plus 3 ugly plus 1 equals 0. All I've done is put u in place of cosine t. And I recognize that as a quadratic equation. I recognize it as a quadratic equation I could solve by factoring pretty quickly. That would factor into 2u plus 1 times u plus 1. And I could fold that back together. And sure enough, it gives me the equation that I started with. I need to learn to factor this trigonometric function the exact same way. I'm going to say 2 cosine squared factors into 2 cosine t times cosine t. Now that I've written it down, I can look at it. If I multiply those two terms together, sure enough, it gives me 2 cosine squared t. I know the 1 has to factor into 1 and 1. And when I fold this out, I've got to get a positive 3 cosine t in the middle. That means both of those 1's need to be positive. And just like I could check this by foiling, I can check that by foiling and make sure it's equivalent to what's on the line above it. When I have it factored, just set each factor equal to 0. to solve those two linear equations. The first one, I could subtract 1 and then divide both sides by 2. I'd be looking for the angles where cosine is -1/2. The second equation, if I subtracted 1 from both sides, I'm looking for all the angles where cosine is -1. Well, I know cosine is -1/2 when I'm close to the y-axis. If I'm close to the x-axis, cosine is going to be square root of 3/2. But close to the y-axis in the second and in the third quadrant, that's where, if this is where x is -1, then these are where x is -1/2. So that's 1626346 or 2/3 pi, and then 465666686 or 4/3 pi. In one revolution of the unit circle, that's the only two angles whose cosine is -1/2. So 2/3 pi and 4/3 pi are the solutions to this first equation. The second equation, where cosine is -1, I know the only place cosine is -1 is at pi radians, right here. So this original equation, I solved it by factoring, and in just one revolution of the unit circle, which is what I was asked for, I got these three solutions. All right. Number 44 says secant beta times cosecant beta equals 2 cosecant beta. That's not a quadratic equation because it doesn't have any squares in it. But we've used factoring to solve equations that weren't like quadratic equations. We could still attempt to solve this by factoring if first we got it in standard form. To get it in standard form, that means set equal to 0, I would just subtract 2 cosecant beta from both sides and pray that that left-hand side would factor. It will factor. There's a common factor of cosecant beta. If I factored out a cosecant beta, what would be left of this first term? Just secant beta. If I factored out a cosecant beta from this second term, what's left? Just the -2. And if we're stopping every step of the way to make sure each line is equivalent to the line above it, I can distribute that cosecant beta and see that indeed it is equivalent to the line above it. I have two factors multiplied together to give me 0. So one of the two factors has to be 0. Those are the two equations that I'm solving. Cosecant beta is 0. Cosecant is 1 over sine. And if I think about what makes this fraction equal 0, there is nothing that makes this fraction 0. If I had 1 over 0, for example, that's not 0. There's no way a fraction with a 1 in the numerator can be made to equal 0. What does that say about solutions to cosecant beta is 0? It means this part of the equation has no solution. If you think about the graph of cosecant beta, it's that series of concave up and concave down looking parabolas. It doesn't have an x-intercept. It doesn't touch the x-axis. There's nowhere cosine beta equals 0. So let's find where secant beta equals 2. Well, if secant beta is 2, then cosine beta is the reciprocal of 2. Cosine beta is a half. And I know that cosine is your x-coordinate, and your x-coordinate is positive in both the first and the fourth quadrant. So where in the first and the fourth quadrant is cosine a half? Well, cosine's a half when you're close to the y-axis. And that's at pi over 3. And in the first quadrant, pi over 3. And in the second quadrant, 5/3 pi. So this equation has two solutions. Pi over 3 and 5/3 pi. Those are the only two solutions to this equation because this equation did not have a solution. All right, just real quickly, last two examples I want to show you are just to show you that sometimes none of the tricks that I mentioned work, and you just really have to think hard about everything you know about math. Number 36 says natural log of sine x is 0. I'm looking for the angle that if I took the sine of that angle and then the natural log of the sine of that angle, it would give me 0. I think my head might explode unless I just look at that as being natural log of ugly equals 0. Where's natural log 0? Well, I could change that to exponential form. I know that natural log means log base e. I don't normally write it as log base e, but that's the same thing. And then in exponential form, that would be e to the 0 equals ugly. Ugly equals e to the 0. What's e to the 0? E to the 0 is 1. So that's how I would solve this little algebraic equation that didn't have any trig in it. I should be able to solve this trigonometric equation the same way. I can say natural log means log base e. And then I can change it to exponential form. In exponential form, the base is e, the exponent is 0, and e to the 0 equals sine x. But e to the 0 is just 1. So where in one revolution of the unit circle is sine 1? In one revolution of the unit circle, sine is 1, where the y is 1, where the y coordinate is 1, and that's at pi over 2 radians. So the solution to that equation is pi over 2 radians. And we can check that by saying sine of pi over 2 is 1. Natural log of 1 is 0 is a true statement. All right, that's enough examples. It's time to jump in there and try some on your own. In the homework on this handout that I gave you last week, the homework for solving trigonometric equations is from the Appendix D3 that I copied for you, odds number 27 to 37. That's these problems, 27 to 37 right here. 27 and 29 say solve in just one revolution of the unit circle from 0 to 2 pi. Notice that 31 through 37 also say solve for just all the solutions in one revolution of the unit circle. So you don't have to worry about the plus 2 pi n or plus pi n on these problems. Optional homework, but I know that because this is difficult, you need all the practice you can get. You can do as many of those odd problems on 6.2 as you want. That's the handout from which I took my example. All of the odd problems have the answer right beneath them. So you can try as many of those as you'd like, as many as you need to, and ask me questions from both sources tomorrow. All right, work hard. Have a good day.